Okay, we're going to be looking at a system where a mass is attached to a spring here. We want to develop a number of equations, particularly the equation for the frequency and the period of oscillation. So we have a frictionless environment. So we've taken a glider that is on an air track, so there's no friction, and the only force that's exerting on the glider is the spring force that's causing this object to oscillate back and forth between these two positions. So now, remember, as I pull the object to the right, there is a force that is exerted to the left, causing it to accelerate to the left here. Now, as the object slides over to the left, the acceleration diminishes. When it passes through equilibrium, there's no acceleration. And then suddenly as it moves to the right, now the spring force is trying to slow it down and cause it to, now the force is acting on to the right, and the acceleration is now acting right. So you want to remember that the acceleration is not constant. A is not constant. You cannot use the kinematics equation. You know, remember x equals x0 plus v0t plus 1/2 at squared. You can't use that in this type of situation because the acceleration is sinusoidal. So let's go through how we figure out how long it would take to find one complete cycle. So you can't use kinematics. You have to come up with another method. So remember Newton's second law, sum of F equals ma. So as the object is oscillatory, the net force acting on it is due to the spring force. So we're going to replace the net force with negative kx. So negative kx equals ma. And then if we rearrange for a, we're going to get negative k over m, the spring constant over the mass of the object, times x. Now you recall hopefully from our earlier discussion of kinematics that the acceleration is equal to negative omega squared times x as a function of time. So remember that when the x was 0, the acceleration was 0. And when the x was at its maximum position, say amplitude a, then the acceleration was at its maximum amount as well. So because we know this is true, that the acceleration is directly proportional to displacement, we can see that this piece here and this piece here must be the same. So the angular frequency for this type of system, squared, is equal to the spring constant divided by the mass. And hence, if we solve for the angular frequency, we get this equation over here. Now earlier, we defined the angular frequency as 2 pi times f, or 2 pi over t. So now we can set, basically, k over m equal to 2 pi over t, and then if we rearrange that equation, we end up with this one. And this is on the AP formula sheet. This is the period for a mass spring system. Now, if you have two masses attached, then you're going to have to change that to 2m. And if you have a couple springs in series or parallel, well, then that becomes a little bit more difficult, and I can talk about that later with you. Now, also, I should point out too, is as the object oscillates back and forth between the two spatial positions, so this is at maximum displacement to the right and to the left, remember over here it will be all elastic potential energy, which we studied earlier. So it will be spring potential energy, which is equal to 1/2 kx squared. When the object passes through equilibrium, all that spring potential energy has been converted into kinetic energy, and so now you have 1/2 mv squared. Now if you're in the middle here somewhere, and the sum of these two energies should add up to the total energy, and noting that the total energy remains constant throughout the whole process. So this is a parabola going this way. That would be the potential energy. You could draw a similar one for kinetic energy, something like this. This would be the kinetic energy graph. So if you're solving any problems where you have to, say, find the velocity given a particular position where it's moving, it's somewhere not at maximum displacement or at 0, then you can use this equation to solve for the velocity. Alright? And so remember that the total energy of the simple harmonic oscillator can be given by this equation, 1/2 ka squared. Why is that so? Well, that's because if this is the total energy at any particular point, when you're at the maximum displacement of x equals, say, positive or negative a, the velocity is 0. So if you take this equation and you set E total equal to 1/2 mv squared plus 1/2 k, but you're going to replace x with a squared, and the velocity is 0, that gives you the total energy of 1/2 ka squared at any point. So the sum of the kinetic and the potential energy at any position would be equal to the total energy, which is given by 1/2 Ka squared. This is the equation you would use for a mass spring system that is oscillating horizontally. Now, if it was oscillating vertically, you'd have to add in also an MGH term. Okay, so you can determine the velocity, maximum velocity, that would occur when the position is 0. So if you take the equation above, set x equal to 0, this term disappears, and then the kinetic energy at equilibrium will be equal to the total lost potential energy at the endpoints, and then you could solve, say, for the velocity if you knew the amplitude and the spring constant and the mass. Okay, so let's put this to practice with the next question.